Okay. Hi everybody. First of all, thank you very much for having me here today. I'm very excited to be in this talk here. Especially thanks to my colleagues who previously introduced more than us, so that will go through it right now. So the name of my talk is advanced modeling, but it's not anything too complex to understand. Today we focus a lot on how to develop data-driven models, especially focusing on the use of spatial and activity data. So I'm going back to the same figures you already saw 20 times today. Maybe you remember, yeah. I switched them recently. So I will start with a question. There is one thing this framework well, apart from being model. So they represent basically some levels of abstraction of human behavior. They focus on essential ingredients, as Daniela explained this morning, that are essential for explaining the behavior you observe in your data. So it depends a lot on your research question. But the mechanisms underlying these models are basically the same. The mechanisms ruling infection and disease progression are essentially the same. And the choice of these frameworks for you basically, in my opinion, depend on two things. 70% from your research question and the data availability, and then it's up to you where to start from the data from the research question, no judging. And the remaining 30% availability depends on the level of details you aim to use, how deep you go into the description of your model. For example, heterogeneities in a population. If you want to reproduce a distribution of a variable in a certain population, you need to implement an individual-based model. What else? They are mathematical models, they simulate mechanism, action, and reaction, so basically this is why lots of physicists like us do this. Mobility and mixing, and so on, contacts and infection. And these two models, these three models, let's say, are very important frameworks, and I will go today more into detail on individual-based models and population models. But notice that actually contact networks are always present in the framework we use somehow. So there are many ways to use mobility data to inform individual and population models. Intuitively, you can think of simple integration of these data sets.
Then you can look at the different age groups and you expect this is the number of infected, for example, in different age groups, and you see that these are the children. They generally have a peak earlier, just because they have more contacts, they get infected earlier. The older people, they have a peak of infection later, so you can characterize all these things. And something which is also really cool is that now we have heterogeneity of the individuals, we have a contact matrix, and the contact matrix is made of different layers. Right? So if you remember, you have the home layer, the work layer, etc., etc. So you can model the impact of targeted intervention. So you can say, what if I close school? Well, you take the contact matrix of school, you modify it, and you run the model. What if I, let's say, advise remote working for some people? Well, you take the contact matrix of the workplace, you modify it, and you run the model. This is what we do here. These again, the spectral values that we have met before, just a number that tells you how intense are the contacts, and we are imagining that at some point we close partially the workplaces, so the contact is down. Here at some point we imagine that we close a school and the contact is down. And we can very easily simulate the impact of this. So this is the number of infection with the contact matrix without any intervention, and the green curves is the number of infection where we are including these interventions. And this can be done. And we can also be more concrete. We can say, by comparing the two curves, we are saying that we are getting 15% of the infections, but we also have basically a peak which is half as before. It's just, let's say, a very quick case study that shows you the potential of this approach. Okay, I think that's 10 minutes, right? Something like that. 15 minutes, that's great. Yeah, perfect on time. So in this last part, I would like to give you an idea of how, what we do in the lab. We have these models, we have these equations. If I have to do it now, live, what do I do? Well, we need to translate this into a computer program, so something that the computers can elaborate. So the question is, how do we simulate this model in practice? Well, we have seen that despite its simplicity, the SIR model cannot be solved analytically. So this means that we need a computer programs to solve the SIR model for us. This is called numerical integration. Fundamental distinctions we have already seen with Daniela: deterministic simulations and we have stochastic simulations. So very briefly, the deterministic simulations, as the name says, they are deterministic. So you give an input, you get an output, and that's it. So for a specific input, the output is deterministic. With stochastic simulations, instead, a single input gives a variety of outcomes because there is noise. This is how reality works in a sense, no? Because it can be that I meet someone, I unfortunately infect that person, but if we repeat this multiple times, then it will not always happen. So there is some stochasticity which is intrinsic, some randomness, some noise, which is in the system. This is what I mean. So this is the number of infected as simulated with a stochastic simulation, which has these gray shaded lines, and as you can see, there is some variability. And the dashed line is a deterministic simulation, which is somehow the average. And the cool part of the, let's say, of any stochastic simulation is that you can compute, as Chiro was saying, uncertainty, which is super important because, I mean, if you have worked with epidemics, you basically know that you can never be certain. I mean, there is so many variables at play that characterizing uncertainty is super important. This is why this is advice: be very careful, and also suspicious about point estimates, about numbers. There is no number, there are no numbers in this business, there are confidence intervals, there are bounds. That's what we do. So, how do we integrate deterministically the SIR model? So there is a method which is called the Euler method, which is a way to take a system of ordinary differential equations and integrate it. So let's go straight to the case study. So this is the SIR model system that we have seen. We remember it, and that's a recursive formula. Because we have already a formula to compute the number of susceptible tomorrow or after delta t times that. And this is a function of the number of susceptible today minus these terms that I can compute it. So if you put some initial conditions, you can apply these things like a sort of a machine, and you can literally compute it on a piece of paper. And so you can use this recursive formula to integrate the system numerically. That's super easy. So, mathematical from a point of view of computer program, this is a for loop. It's super easy. This is what it looks like in Python. So it's literally a for loop. So, as we said, you need to set the initial conditions. This is an input that you need. And then you just iterate, you compute the dx, the I, and the r. You update and you repeat. That's it. There are problems, of course. Choosing that delta t is not easy. This is a problem called the stability of the solutions. So if you choose a delta t which is really high, your simulation will be faster because you are simulating, let's say, week on week. That's super fast, but the simulations will be unstable. For example, here the orange line, you see at some point it becomes even negative, that's not possible. I mean, it's a number of infected. I cannot have -10 people, and that must be possible. But it can happen if you don't choose the right delta T. And there are a lot of methods to overcome this problem, but that's not the total. Stochastic simulation. That's what I like the most, and this is why we expand in the next 10 minutes. It's going to be quicker, I guess. So, if you want to simulate a stochastic model, stochastic SIL, you need to use what we call chain binomial processes. That basically it works like that. So, at each time step, you need to simulate the people transitioning from one compartment to the other, and this is just a sample from a binomial distribution. So it's the same as before, but instead of applying the Euler method, we do a binomial sample. And this is how we introduce stochasticity into the model. And this is why we call chain binomial processes. And this is a stochastic model, the SIR stochastic model. Again, initial conditions, we iterate, and then we do the binomial sample. And we update, and we repeat, etc. Or you can use software tools that does this for you under the same hood. And this is a possibility. This is something that we have developed at ISI. It's a Python package that basically allows you to develop the model that we have seen also with the social structure, the contact matrices, the interventions, all these things, without having to code the system of equations yourself, without having to write the simulation algorithm, etc. And for those of you who will attend on Wednesday, we will do a session on this. We can do many things. So, for example, we want to define a stochastic SIR model. So you simply say, okay, I want a model with these three compartments. I have two transitions. One is the infection which is mediated. One is spontaneous. Run the simulation from this date to this date to have the results. And this is the output. You can introduce the contact matrices, you can plot them, do the same thing. For example, you want to apply the model for Thailand, you simply import the population for Thailand using one line of code. The model will be applied to the population of Thailand, the contact matrices of Thailand, and it will run output results which are compatible with the population of Thailand. Then we can do model calibration. This is something we also said before, it's super important. So you have some data and you have a model, and you want your model to reproduce that trend. And with this package, you have built-in Bayesian approaches, advanced Bayesian approaches, to basically calibrate the models to any data. And once you calibrate the model to the data, then you can run forecasts, you can run projections, and test the different impacts, for example, of reopening strategy. So what if I do this strategy of testing, etc. And you can estimate the parameters. You can estimate the porphyria distribution of the parameters. This is the R0 of COVID-19 in Massachusetts in a case study. You can do a lot of stuff. That's the end of the talk. Thank you very much for your attention.
Okay, thank you very much for my very interesting talk. It can really be generalized. So, do you guys have any questions? Yeah. So, if I have a vaccine, so how can I model the vaccine efficacy? Should I reduce the data, the delivery, or add a new variable?
If I got it correctly, is how you model vaccination, like vaccine efficacy, is that right? Okay. Yeah, you can do it quite easily. We find it here quick. So this is an example. So we have This bottom row here, this is a simple SLR model. And then we have one line for the susceptible individual who received the vaccine. And as you can see, basically they get infected at a rate which is not beta, is beta times 1 minus VE, where VE is the vaccine efficacy. And then you can build even more sophisticated things where you can include multiple effects of vaccines. Not just the protection against the infection, the protection against severe outcomes in case of breakthrough infection or reduced infectiveness. You just need to introduce these terms that modulates, for example, all the other parameters. But it can be done, yeah, absolutely.
Right, thank you very much. I actually forget that we will have time for now. Do we? Okay. Yes, we have time for one more question, but if you have other questions in the session at the end of the day, cater for Q&A.
So I just want to know what is the most, like you have explained how we create a model. I want to know what is the most common problem you face when you create a model, and how do we validate that it can be used?
Cool. Okay, that's a bad question.
I mean, you can give a short answer and you can elaborate on that.
Later.
Yeah, later.
I'm super short. Problem, data. Problem is the data. How do you parameterize the model? And this is linked to your second model. So how do I validate the model? You need the data. So it's, let's say, a feedback loop which is quite, I mean, this is where the problem is. Because model-wise, we can do very complex stuff. That's not the problem. It's also if you have computational power, which today is cheap, then building the model, that's not the problem. Then how you make the model and produce the real trends and validate that, that's a problem that is linked to the availability of the data, which I think it's one of the most common real-world issues. But I can elaborate more on that if you want on the coffee break.
Alright, thank you very much. Don't forget that we have more time today for the Q&A session. But for now, we're going to take a break for 20 minutes. Yes, and we will start the last lecture of the day at 10 to 3. Okay? Thank you very much.
So the model is, we have to model first the section of cancer individuals. And we rely on the clinical survey that was released in 2015. This survey individuals had to declare the number of sexual partners they had in the last month, and if they attended sexually commercial events like clubs, sauna, battles, or even collaborative. Finally, they had to declare their age. So this is an example of the distribution of the number of partners of MSM individuals visiting clubs and events. As you can see, it's power law. So we can sample this distribution to the power law and extract individuals with the number of sexual partners. And finally, we want to compare this distribution. What we get is a network of 9,027 individuals, 5 replicas, group of this, which each node is an MSM individual linked to sexual interactions. The interactions are daily. There is large variability in the number of sexual partners, as you can see in the red dots. So the data from the relevant survey, while in blue the distribution we get from these sexual partners. So now we can simulate the spreading of mpox this is a model very similar to what I showed you before with vaccination. We have susceptible components, susceptible become exposed. Exposed can divide in infected, detected, or infected and detected. Infected and detected are here. We don't have any data on them, so they are useless for us, so we just send them to the code. While infectious detected, they're actually the data that we get. So the number of detected cases of the day is the compartment we want to fit. And these detected cases, at some point, we isolate. So this is another compartment in which detected, infected, isolate, environment, and finally they are coded. We inform this model with an average onset to isolation period that will fit from the data, from the libraries data we got from scientific plants in the first month. And as you can see, the onset to detection, which is also onset to isolation in this model, decreases with time. So empirically we see that it took more time to detect positive cases, while in June it went down to 7 days, and finally in July, when the epidemic really increased, it was almost 6 days. Of course, the population that we had in the model is not completely naive and susceptible. We have individuals who were already vaccinated from smallpox. The smallpox vaccination was 71% effective against infection from mpox. We had 47% of the individuals in the survey to be individuals over 42 years old, meaning that these individuals were already vaccinated and covered from smallpox vaccination. This is our background immunity. Then we had the post-exposure vaccination that took place between May 27 and July 10, and was given to n past contacts occurred between the onset of symptom day and the detection day of the pathogen surveillance days. This post-exposure vaccination was estimated to be 89% effective against infection, and it was effective 14 days after administration. Finally, there was the all-type vaccination campaign, the exposure vaccination. It was the vaccine was 78% effective against infection, and again, it was effective on 2 weeks after the administration. So let's say we want to model this type of behavior. So let's test the last hypothesis. Let's say the community responded by cutting the number of sexual partners they had in the period because they were scared of the epidemic. So every day we model there is a certain percent of MSM that we want to fit. It starts to reduce the sexual activity by a certain percent, also to be fitted. Non-vaccinated MSM, let's say those that are not vaccinated from smallpox, change behavior, breast donor. And this is how we implement it in the network model. So we have the MSM, which have the nodes in the network. We say this guy stops sexual activity during this period, and it chooses any contacts to cut the relationship. Finally, we also model what is the period in which this behavior occurs, and this can probably occur in this phase, because this is where the epidemic starts to peak and finally decline. So how do we choose which start reducing their sexual behavior? We have 3 hypotheses to do this. One is that everybody do it before, doesn't have anybody. The second one is that those with the highest number of sexual partners do it first, because they feel more exposed. And the third one is that only the case contacts, so those that became in contact with the positive case, change the behavior. And the best fit model actually is, spoiler, the model in which we assume all the MSM change the behavior uniformly. And the result of this model is that half of the community, 49% of the MSM in our model, reduce their activity by 93%, resulting in overall 40% of overall contacts, sexual contacts, occurred between mid-June and the 20th of July. This model says that if this change of behavior would not have occurred, we we would have had 70% more of the cases reported. And as you can see, here is the steep curve that we can model. Here is the cumulative trend with the dots being the detected cases. The blue line over here is the detected cases in our model. And the dashed line is the total cases including the undetected of animals. And in this third panel, we see the number of avoided contacts in time in our model. So you will say, okay, all good, this is very nice, but how do you evaluate the results? Is it actually true that people change their behavior? Less people, more people. So in a post-outbreak survey, 23,000 respondents, of which almost 4,000 were multi-sexual partners, 27 living in the Paris region, and they declared that actually 46% of them were just homosexual partners in that summer. So the results of the model are in line with the post-outbreak survey results. Still, that will show estimated that, again, the behavioral survey, most of the individuals living in Western Europe declared that change of sexual behavior because of mpox between May and December of the same year. Okay, let's test what if this was actually not the case. What if it was not due to a change of behavior in the MSM community that suddenly brought down the epidemic curve? Well, let's say it was because of the post-exposure vaccination. So we now fit the model with and without post-exposure vaccination, and we see what is the effect of this vaccination in our this prophylaxis in the model. And as you can see, the epidemic curves that we get are essentially the same. So we are pretty confident saying that actually it is not to happen. And post-exposure vaccination did not have a clear impact on the curve of the epidemic. Let's test the final hypothesis we made. Let's say we actually saw a very small fraction of the epidemic, and the rest of the cases were undetected. And the rest of the cases in possible depression susceptible, so almost most of the MSM in the Paris region got infection and didn't got detected. So if we do this, we get really realistic results of the parameters of detection, resulting in only 4% of the cases being detected, with an overall epidemic size is very unrealistic, 30,000 total infection in 1 million. So in conclusion, in the study, we understood how the changing behavior of half of the MSM community in the Paris region, resulting in a avoidance of 90% of sexual contacts, that explains the carbon of the epidemic in the Paris region of mpox, avoiding 3 times more cases than what we actually observed. And this was in agreement with the post-outbreak survey estimates from another survey on behavior of the MSM community called CARASO. On top of this, we found that the post-exposure vaccination or also the depression susceptibles were not a realistic hypothesis to explain the reduction of infection in a so fast manner. This is likely due, especially for vaccination, likely due to the limited number of doses that were available in the early phase of the outbreak and the challenges of contact tracing, because not all contacts could be recognized systematically. Finally, the vaccinated exposed individuals at the case contact vaccinated with the post-exposure vaccination, only 83% of them received their doses before the full day they recommended for public health. So in perspective, promoting the risk behavior reduction is should be favored in highly active individuals. If this change of behavior occurs in the most exposed individuals, we would have needed only 20% of the MSM to reduce the sexual behavior. But actually, it had to be 50% of them to respond without priority to higher exposure. And the large spontaneous change in behavior will not be sustainable in the long term. However, the WHO estimated that 23% of the LSM in Western Europe. We're still reducing the sexual activity 1 year after the first time. Now I would like to ask you another experiment. This is actually a work in progress. The research question could be, what is the effect of school closures on the total epidemic of the city? So one way to model this would be to have an agent-based model. How do we build this agent-based model? Well, we have to create a synthetic population. And this is an effort that we are doing within the Siesta European project in collaboration with ISAL and from Spain. And in this project, basically, we aim to create a steady population for Italy. And to do this, let's say we take the map of Italy on the right. And let's say we take a city. Let's say this is Turin. And from the census, we have demographic data at the census tract level, like the age sex pyramid of individuals living in each census tract. We have the distribution of household sizes, and we have the configuration of these households, like the age and sex of the individuals belonging to these households. From this simple data on the households, we can build some simple contact matrices that only represent contacts within the households, as Nicola showed before. So let's say individuals live in the households and they have these contacts. But these are not the only contacts they have every day. They also go to work. So at work, they will do the work shifts and meet with other co-workers. And the co-workers will give rise to other contacts. And finally, these contacts can be represented to another contact matrix that we build from the activity of the agents. And after work, probably we will have some leisure time, we will play bar, we will have some friends. And the same process can be done for children. Children go to school, they only need to go under the human source and the children. And in the end, we will end up every day with a set of contact matrices describing the contacts that the people in the synthetic populations have done. And this would allow us to build us models on the basis of an agent-based model. So the important part of this framework is that at this point, if we want to introduce policy, we need to define the entire model. We just close the schools, and the agents will learn that we have to go to stay home. And if the children stay home, then also the parents will stay home and so on. And we don't have to make our assumptions of what the behavior of the agents will be. So this framework is very interesting because at this point we can build age structure models, but we can also turn these into meta-population models. So once you have the time activity and proactivity of the agents, nothing stops you from doing this, not only Turing, but also in land, in Rome, in the entire company. And at this point, we can use these as a basis to building meta-population models. And this is very interesting because at this point we have a very powerful framework that is based on individual features. And we can study what are the results in epidemic inequalities of disease spread, what is the disease spatial invasion, what is the effective intervention of specific demographic groups, especially when it goes to specific settings and so on. So at this point, I will tease the population models. So let's start talking about what are the population models. I will explain this morning, so we have to convince you again of the practical utility of these kind of models. And in general, let's say they study the spatial spread of disease, and typically we want to understand what is the effect of travel, importations, and travel countries on the epidemic spread. I will show this morning how this framework was already used to forecast the H1N1 peak in 2009, how they estimated the most probable origin of the pandemic, and estimate also the impact of travel bans in a successive subsequent study in 2014. We already talked of GLIM. It is a powerful tool. It is an expert tool actually that can be put in the hands of the public and the very experts to play with the models and understand the implications of travel bans and also the implication of importations of things worldwide and how the air traffic works. So these models are typically formed with origin destination matrices like traffic from international travel agencies, community, and so forth. These are typically given at temporal scale. For example, the air traffic network times replicated already at a monthly scale. Some other types of data can be aggregated at a higher temporal resolution. So there are multiple kinds of data ingestion. This framework is very flexible to the type of data that we have. But we can also go to finer grained spatial solutions. For example, let's say I want to model an epidemic running in different urban contexts, different urban structures. We can use origin destination matrices to let individuals move across the city and spread the disease, and then change the structure of the city actually the structure of the city and how people move, define how the epidemic spreads within the city. And this can be done with the population model. The second research question is to study the effect of multiple interpretations on the local epidemic. For this, we can take origin destination matrices, where individuals move now across the country at a different distribution. We don't have city blocks, we have provinces. And we can see the effect of city for the specific origin of the epidemic on the local communities and how this affects the intensity of the other destination. So this is a data population model in which actually we make a step further here, a layer of complexity and model also the social network and the sub-population. So the first study is a study that we did in collaboration with Google in 2022. In the study we had already built on previous research that we did, in which we already observed that cities worldwide observe of a continuous spectrum of the urban hierarchy. And for urban hierarchy, just to simplify the things, we have cities like Los Angeles, which they have mobility hotspots spread all over the surface in the urban area. On the other side, we have very compact cities like Paris, in which the mobility hotspots concentrates in the city center. These are typically most of the European cities built by the Romans. So the mobility data that we got from Google are origin destination matrices encoding trips between S2 cells within 22 major US cities. S2 cells have a resolution of around 5 square meters. And then we have epidemiological data. There's the number of cases reported daily at the county level. In the biggest metropolitan areas like New York, we have between 15 to 20 counties. And at this point, we have an interpopulation model in which we don't have counties, we have urban blocks. And the trips from one block to the other is given by community mobility and the mobility they get from the. So the first observation that triggered our research question was basically two trends. On the left plot, we see how compact cities like New York at the beginning had a weak association with a higher effective reproductive number. So we said before the R0 and the R0 is the effective reproductive number where the population is completely naive. And if the population is not completely naive anymore, then we pass to another description of the epidemic spread, speed, which is the effective reproductive number. So there is a weak association between the speed of the spread of COVID-19 in the first wave of 2020 in US cities. On the other side, we have the compact cities in the right plot show the higher case incidence rates. In yellow, we have the cities that are really experiencing the epidemic peak and the epidemic curve is going down after May or June. While in red, these were mainly cities in the south in which the epidemic did not unfold as intensely as on New York or other East Coast cities. So the question is that are we seeing just a correlation, or is there actually a mechanism explaining for this impact of the urban structure of the epidemic? So we want to model the effect of urban structure to answer this question. The problem is that we live in so many cities that actually have very big differences between them. There are multiple confounders, for instance, to cities that we observe. If you took more, it would be even worse. It could be the urban shape, different demographics, the urban land use, they are all different cities. So what we want is multiple representation of the same city, maintaining all these things, but changing the mobility structure within the urban parts. So to do this, basically we random swap fraction of leaves in the urban mobility network until we get to a very low hierarchy network. So just to give you an idea, we pass from having Paris, and then we shuffle the links until Paris looks like Los Angeles, let's say. So at this point we have a complete spectrum of hierarchies of the urban structure, but it is still the same. Then we use an economic model. In this case, again, we want to be according to this, what I showed before. And typically, the force of infection is encoded by this thing here that I showed before, in which you have the transmissibility rate multiplied by the density of infection. But here, the mobility is not explicitly defined, so we use a population framework that actually considers the mobility within the force of infection itself. And we just need to know that the force of infection felt by the urban block I is the result of the force of infection felt by the individuals in I because of the infected in I, from the individuals of I because of the infected coming from J, and the second term is given by the susceptibles of I going around the city to other J's, meeting the infected destination. So in general, if we take this snapshot of the people in Bangkok now, we don't have exactly the census population of Bangkok. We have an infected population given by both the census population and the commuting rates of individuals coming to Bangkok to work, and on top of that, the individuals of Bangkok going away from the city to work. So once we run this model on these synthetic replicas of the cities, we observe again that we recover a cleaner trend with respect to the data we observed that explains at least the relation is actually between the R-affected and the hierarchy of the urban structure. It's actually different when we model the epidemic in a sprawl city or in a compact city. And again, also the incidence peak is higher for more hierarchical urban structures. So this makes sense, and this is not the only thing that we observe. Consistently with the higher are affected, we also see that the time to peak decreases with the urban structure, and at the same time the final size decreases. So these are all consistent results. So now that we reproduce this, we were around the end, and when the data that we observed regarding the first wave of COVID-19 in the US. So we know that in the US, different cities have different lockdowns. This could be also due to political reasons. But we didn't want to go in that direction. We wanted to make the hypothesis that this actually depends also on the urban structure. So we implement a lockdown in this model, in which we parameterize the number of individuals staying at home completely isolated, which is excess. And we test excess from 0% to 80%, representing a very hard lockdown. And we implement this in the first infection. And the result of this is that when we apply a mild lockdown here, with only 40% of individuals completely isolated, and we do this pretty late when the incidence of the cities are really reached many individuals, say, then nothing changes about respect to the non-intervention scenario. So basically, this is too late intervention to change the scenario we already observed in the non-intervention situation. But if we use a very stronger lockdown, let's say now 80% of individuals are isolated at home, and we do this very early in time, then at this point the picture changes completely. And what we see is that compact cities respond better to the lockdowns with respect to sprawl cities. So, as a wrap-up in this study, we found that compact city structure seems to favor the spread of infectious diseases, where the risk of observing the data. So it seems like more hierarchical compact cities favor more let's say, faster disease spread of respiratory diseases. And however, if the mobility restrictions are not too weak and not too late, and are applied sufficiently early, then the compact cities seem to respond better with respect to the smaller cities. So in perspective, it seems like the way we build the cities impacts the they host. We should pay attention to how urban structure and urban planning is done in our cities. And on another note, from a public perspective, the surveillance on compact cities should be prioritized with respect to others because they are more susceptible to these outbreaks. The last study I want to show you as an example of the population model is actually not in the US anymore. It's a study that we did in Spain when I was working at IFIS. And in this case, we want to study the effect of multiple case importations on the intensity of the local epidemic. So there were some press releases that triggered a question, basically. So let's say that our sources from the newspapers. So a case was mentioned at the beginning of March 2020 that the uncontrolled spread of coronavirus in Spain forced a change of scenario. Basically, what happened in that week was that Madrid, the region of the capital, decided to close schools and universities 1 week before the nation lockdown. So there was a lot of criticism on this move because basically the administration of the region got attacked because probably many students of schools and universities already left Madrid while the outbreak was already developing in the city. And this probably, let's say, in the public opinion, this could have been the reason why a lot of cases were reported in the forthcoming weeks in the rest of the provinces. At the same time, another newspaper coverage was focusing on the epidemic developed in very rural areas of Spain. So just to mention the last press release here, provincial authorities reported in April 22, just 10 days after the lockdown, 1 month and 10 days after the lockdown, that the population infected in Soria, which is a very rural province, was already 3 times that population average. So this also had an impact on the local community because the demographics of these rural areas are much older than the rest of the city as a community. So our question was at this point, could it be that this picture on the left representing the cumulative cases of COVID-19 1 month after the lockdown could relate to the mobility from Madrid? To answer this, we consider the mobility received the population, the per capita number of trips received from the capital in each province in Spain, and we wanted to relate this to the peak of the incidence registered before the lockdown. And as you can see on the left, the picture is a bit noisy. We have some correlation, but I'm not really sure if this is true or not. On the right, actually, when we look at the mortality, or the number of reported deaths due to COVID-19 with respect to total population, and the trips per capita received from Madrid, then the picture gets a bit cleaner, and we can see some clearer trend. The reason why the problem on the left might be that noisy could be because of different factors and confounders, maybe from different under detection, different case infectation in each region, different case reporting, and so on. So, okay, we saw simple correlation, but this could actually be due to other factors. It could be because of distance, it could be because the epidemic started earlier, it could be because of population density, and so on. So in this case, we repeat the same regression, but now as a multivariate regression, in which O represents the multivariate regression, and we compare it with the univariate regression for each of the cohorts. And we see that actual distance does not explain the variance in this at all. A little bit in mortality peaks, but most of all, mobility is what explains the mortality better than any other provider. And the onset, in case, is still related to the mobility, because as we know from the population model, the earlier you move from the place, the earlier you affect the destination rate. Now we perform some sensitivity tests on what is the origin of the epidemic, because up to now we take for granted that Madrid was the origin of the epidemic, but it could be somewhere else. So to do this, we perform a correlation again on incidence and mortality, using as the origin of the epidemic any other province in Spain, and we actually confirmed Madrid is the one with the highest score. And now we decided to extend this to other 4 countries in Europe. So at the beginning we started with Spain, because we had data. So as I was saying before, we started with the search question, we started with data. In this case we had both 2 already. And these data were provided by Dynamics, and they represented mobile phone data. So in this case we had devices moving across provinces, aggregated in knowledge and distinction analysis at a daily scale. And then there was this program called Data for Good that Cubic released right after the start of the pandemic. And with this data, we were able to model the same effect in 5 European countries, including Spain, the United Mobility Source. And comparing the mobile devices with cubic data, we actually found the result almost the same. But the important thing is that we observed the same effect in all 5 countries. And looking at where the epidemic should have started, confirmed many prevalence studies released after the first outbreak of COVID-19 in 2020, or news coverage, that was the case for Germany. So in Spain, we can see again the source of epidemic starting in Madrid, in Italy, mostly spread from Milan, in Germany from Bavaria, in France from the region and west. And these were also confirmed by prevalence studies. And in England, it turned out North France responsible for the start of the city. So, okay, we saw this from the data, and it's all very interesting, and it could be also that this is not due to the mobility. So let's make a model and understand actually if there is a direct effect between the mobility and the seeding effect to destinations. So again, we use the same model for COVID-19 that I already showed before, and now we use a data population model in which we have each patch is a Spanish province, and we have the mobility between the Spanish provinces everywhere. Now this is a meta population model with a reduced population. It's actually we instantiate individual features in the individuals, and I will come to this in 1 minute. So the Spain population is represented in the scale 1 to 500, divided into the relative provinces. The mobility data that we use is origin distribution matrices from devices between March 1 and April 14, 2020. And we instantiate 10 cities, 10 initially infected in the capital of Spain, Madrid. And then we simulate the spectrum of month and see what happens. So this is the case in which I show you how exactly we implemented the mobility in a model. But this is a different framework than what I showed before. So the tricks here are instantiated by switching to individual's position in the locality population. So here again, we have, just to make this clear, we have the meta population model in which we have every patch which is a province, and within each patch we have a social network structure. It could be a great, very wide, or a well-mixed network. And these are very known frameworks for network scientists, because basically this is a regular lattice, this is a wire which is mobile property, and this is a well-mixed, basically an homogeneous mixing in which a very targeted change the people with which you interact. And now we test the effect of seeding these 3 topologies. So we start with a simple population model. Let's say this is only Madrid. There is no mobility, there is no responsibility, there is only Madrid. And here we see that the increase after augmenting the number of initial infected in the three topologies gives rise to different incidence peaks. So, for example, we see that the grid social network for the small number of seeds gives rise to very small incidence peaks. This is because if you think to the grid and how it works, you are an individual in the grid. Here. If you are an individual in the grid, in the same instance, you are here, you have these 4 friends, and you have nobody else. So if you manage to infect them, the epidemic spreads. If you don't, the epidemic stops there. So that's a bottleneck effect. Similarly, also the wild grid allows some long-range trips. So again, here you are in a grid, but you have some long-range wiring, so you are able to reach people a little bit more far away. But again, it doesn't change much unless you rely on a very high fraction of the links. And finally, we have a well-mixed population here. It's hidden, but it's flat. So there is no effect on the well-mixed population of this multiple seeding. If we pass to a two-population system, let's say now we have Madrid and Valencia. So Madrid is the source of the epidemic, Valencia is the seeding population. Here, we have a case in which we have 1 seed and one in which we have 5 seeds. And this is the grid of the social network of Valencia. So this is time 1, time 2, time 3. You see, if you only have 1 seed, you have a good bottleneck because when you spread far away from where the seed is at the beginning. This is, let's say, a social network model like a grid. And if you have 5 seeds, then you can reach a much higher level of infection in the population. And this is what we actually observe here. So if you have 3 seeds in the grid, or 24, that doesn't change much. You are stuck there. But if you have a well-mixed population with 3 seeds, 24 seeds, doesn't change much. The epidemic progression, because the size of the epidemic stays the same, and if you have 3 seeds or 24 seeds in the grid, and it changes a lot, the speed. As you can see, 24 seeds are much more effective at affecting the whole population, as indeed we observe here. So if I now cut this here, you can see that for the well-mixed population, it doesn't change much, but for the grid, the final size at that time changes a lot. So now we can pass to the full system in which we model exactly the entire country, not anymore only 2 populations. And here we want to observe what happens if we let the epidemic grow up to infinity. So if we let them grow up to infinity, it doesn't matter much the topology of the social structure that you model in the subpopulation. They will all get to the same, more or less, to the same epidemic size. And this is not our theory, this is okay. But what if we implement a lockdown? And here we have a very extreme case in which the lockdown is completely total travel ban and half visibility as to limit social distancing. So now the situation changes. Once we implement the lockdown, we are able to see the heterogeneity of the epidemic sizes in the local regions. So non-intervention means the local epidemic reaches the same size as all the others. But if we implement the lockdown, we stop completely the mobility, then all the epidemic coupling gets to zero. There is no more spatial coupling. There is only independent epidemics growing independently from one another. They only depend on the initial seed they receive with respect to their local population. So, what we see from here that multiple seeding corresponds to more intense outbreaks. And to understand where this happens, just look at this picture. On the left, we have the early phase, the seeding from the capital. And here you see, if you have a social network estimation, the more seeds, the higher the epidemic size of which in a shorter time. If you impose a lockdown, the seeding received by the local estimation stops there. At that point, you can see clear relation that we already observed in the data, for which the number of seeds received by the total population correlates with the peak of incidence, with the intensity. If you don't put any lockdown, you just let it grow, then you don't stop the coupling, lockdown doesn't stop the epidemic coupling, and the individuals circulate freely, even infected, at the point you reach the theoretical limit for the epidemic size in the world population. So in conclusion, what we found is that a higher mobility from the epidemic hub means a higher seeding to peripheral areas and more intense outbreaks. This trend was actually clearer with death with respect to reported cases. The demographics matter. It's not a parameter that we can use and oblige. It's because of equal seeding produces more intense outbreaks in small population. And again, the number of seeds over the receiving population determines the intensity of the outbreak. Finally, the lockdown saw the seeding, because in this case it cuts the epidemic coupling. Our case was an extreme scenario. We wanted to test what actually could happen if we allow the lockdown to be as efficient as possible. Of course, the reality is not like that. This is an extremization. But just to understand that when you cut the epidemic coupling, you get independent epidemics, and this allows us to observe spatial heterogeneity given by epidemic intensity proportional to the seeding. So in perspective, the mobility hotspots, as in the case was Madrid, the other main transportation hubs like Paris in France or Milan in Italy, should be prioritized in surveillance because once they are seeded, as soon as they are seeded, as soon as they will see other places. Mobility intervention, despite they are not able or capable of stopping the spread, and we saw that this is actually impossible. Mobility network topology, they are still important to curb the epidemic and gain time to feed prevalence and reduce the other intensity on the exposed areas. As in the case of Spain, we observe the rural, small communities that are highly connected to the capital experience very high intense outbreak. And the assumption that we make finally on the interaction within the population have a non-negligible effect on the outbreak intensity. So having a metapopulation model assuming that a homogeneous mixing within the population may oblige some effect of the city on the social structure. So this was a little bit of let's say, a general overview of how we can use mobility data to inform individual-based models and metapopulation models. We see different levels of abstraction today. We use them to resolve or answer partially some public health or theoretical questions. And we saw this from different contexts like behavioral change in communities, protection in the airports, and so on. But we have more questions to answer. The problem is that the type of data that are available nowadays is mostly the same as opposed to the pandemic. The type of data, not the amount. We have less accessibility nowadays with respect to what we have through the pandemic. Many data for good programs are now being cut. We only want to rely on our plans that we have for good programs. So the challenge is that so far, we're still missing something to fully understand how this is spread and how population responds, and the pandemic is showing our limitation to understand this. So more than different data may be needed to tackle this challenge. The problem is that what other data do we need? How do we prove that we need some data if we don't have it in the first place and we cannot model its effect on the epidemic? The third more provocative question is, do we really need data? And the final question I will debate is there a limit to the data we can integrate in a realistic model, or have we reached what we could do so far? This is all. Thank you very much. I hope you can talk, and if you want to ask me your question, now or